In the present module, we shall discuss two important theorems of estimation theory. In the first theorem, we shall prove that if a minimal sufficient statistic exists, then a complete sufficient statistic is minimal sufficient. But the converse of the theorem is not true. Next, we consider another very important theorem which is known as the Raw Blackwell Theorem. In Raw Blackwell Theorem, we shall show that how one can improve an unbiased estimator using a sufficient statistic. Some examples will be discussed in this connection. First, we shall discuss a theorem relating to complete sufficient statistics to minimal sufficient statistics. If a minimal sufficient statistic exists for a family of probability distributions, say script f equals to f theta, where theta belongs to script theta, then a complete sufficient statistic is minimal sufficient. Let us consider a proof of the theorem. Let T star be a minimal sufficient statistic and T be a complete sufficient statistic for a parameter theta or for the family script f. Now, we have to show that T and T star are equivalent. As T star is minimal sufficient, it is a function of every other sufficient statistic. Hence, T star equals to HT is a function of T. Now, we define phi t, which is equals to T minus expectation of T given T star. Since T star is sufficient, expectation of T given T star is independent of theta, and hence phi t is a function of T only. Now, expectation of phi t is equals to expectation T minus expectation T given T star, which is equals to expectation of T minus expectation of T. Here we use the theorem of conditional expectation, and finally we get expectation of phi t equals to 0 for all theta. Since T is complete, this implies phi t equals to 0 almost everywhere with respect to script f. This implies T equals to expectation of T given T star. We write this as H star T star. That is, T is a function of T star. Hence, T and T star are equivalent. It is interesting to note that the converse of the theorem 1 is not generally true. We present a counter example which will show that a minimal sufficient statistic may not be complete, as the following example. Okay. Let x be a random variable with PMF f theta x equals to theta if x equals to -1 equals to theta to the power x into 1 minus theta whole square if x equals to 0, 1, 2 up to infinity, where theta lies between 0 and 1. Clearly, x is minimal sufficient. Let psi x be any real valued function of x, then expectation of psi x equals to 0 for all theta will imply theta into psi minus 1 plus summation over x from 0 to infinity psi x into theta to the power x into 1 minus theta whole square. This is equals to 0 for all theta. This will imply summation over x psi x into theta to the power x. This is equals to minus theta into psi minus 1 divided by 1 minus theta whole square. If we expand 1 minus theta whole square in a power series, then after some algebraic manipulations we get minus summation over x from 0 to infinity psi minus 1 into x into theta to the power x for all theta. Comparing the coefficients of theta to the power x from both sides of the identity, we get psi x equal to minus x into psi minus 1 for x belongs to the set 0, 1, 2 dot dot dot. If psi minus 1 equals to c not equals to 0, then psi x equal to minus cx for all x belongs to the interval minus 1, 0, 1, 2 dot dot dot. That is, psi is non-zero with positive probability. Hence, the family of distributions with PMFs set of all small f theta where theta belongs to script theta is not complete. Now, we consider another theorem, which is theorem 2. Let u is a function of x1, x2 up to xn, be an unbiased estimator of a parametric function g theta, and capital T be a sufficient statistic for theta. Consider a function phi t of capital T such that phi t is equals to the conditional expectation of u given capital T equals to small t. Since t is sufficient for theta, it is independent of theta. Then phi t is itself an unbiased estimator of g theta. Moreover, variance of phi t is less than equals to variance of u for all values of theta. This is known as the Raw Blackwell Theorem. We consider a proof of this theorem. Since phi t is a function of t that is free from theta, hence phi t is a statistic. Now, expectation of phi t equals to expectation of u given t, which is just expectation of u, and this follows from the theory of conditional expectations, which is called the tower property of the conditional expectations, and hence we get expectation of phi t equals to expectation of u equals to g theta for all theta. Hence, phi t is an unbiased estimator of g theta. To prove the second part of the theorem, here we use another theorem on conditional variance, as variance of u equals to just expectation variance u given t plus variance expectation of u given t. This is just expectation variance u given t plus variance of phi t. Since expectation variance u given t is greater than equals to 0, it follows that variance of u is greater than equals to variance of phi t for all theta belongs to script theta. The equality sign holds if and only if the second part, that is expectation variance of u given t equals to 0 for all theta, which will imply expectation u minus expectation of u given t whole square given t equals to 0. After some simplifications, we get expectation u minus phi t whole square equals to 0 for all theta, and hence probability u equals to phi t, this is equals to 1 for all theta. The technique of improving upon an initial unbiased estimator g theta is referred to as Raw Blackwellization in statistics literature. An attractive feature of the Raw Blackwell theorem is that there is no need to guess the functional form of the improved estimator. The implication of the Raw Blackwell theorem is that as an unbiased estimator based on a sufficient statistic t will always have a smaller variance than one which is not based on t, the search for a uniformly minimum variance unbiased estimator, that is UMVUE, may be restricted to those unbiased estimators which are based on T. Now we consider some examples. In our first example, we suppose that x1, x2 up to xn are IID binomial random variables with parameters 1 and theta. Hence, the PMF is given by f theta x equals to theta to the power x into 1 minus theta whole to the power 1 minus x if x equals to 0 or 1 equals to 0 otherwise. Here we consider the function g theta equals to theta. Clearly, x1 is an unbiased estimator of g theta. Now we know that capital T equals to summation over j from 1 to n xj is sufficient for theta, since f theta x belongs to the one parameter exponential family. Now we define phi t by phi t equals to expectation of x1 given capital T equals to small t, which is just probability x1 equals to 1 given summation j from 1 to n xj equal to t. By definition of conditional probabilities, we get phi t equals to probability x1 equals to 1 intersection j from 1 to n xj equal to t whole divided by probability j from 1 to n xj equals to t. The numerator can be simplified as probability x1 equals to 1 intersection j from 2 to n xj equals to t minus 1. Due to independence, we can write the numerator in the two factors. One is probability x1 equals to 1 and the other is probability summation over j from 2 to n xj equals to t minus 1. Since the distribution of summation xj is binomial, after some algebraic manipulations, we finally get phi t equals to t by n. So, phi of capital T equals to capital T by n, which is equals to 1 by n summation over j from 1 to n xj, is an improvement of the initial unbiased estimator x1. We consider our second example. Suppose x1, x2 up to xn are IID Poisson random variables with parameter theta. Therefore, the PMF is given by f theta x equals to e to the power minus theta into theta to the power x by x factorial, x taking the values 0, 1, 2 up to infinity equals to 0 otherwise. We consider the parametric function g theta, which is probability x1 equals to k, which is equals to e to the power minus theta, theta to the power k by k factorial, where k is any non-negative integer. We define a random variable u which takes the value 1 if x1 equals to k equals to 0 otherwise. Clearly, u is an unbiased estimator of g theta. Since f theta x belongs to the one parameter exponential family, here capital T equals to summation j from 1 to n xj is sufficient for theta. Now we define phi t. This is just expectation of u given capital T equals to small t, which is again probability x1 equals to k given capital T equals to small t. Using the theory of conditional probability, this can be written as probability x1 equals to k into probability summation over j from 1 to n xj equals to t minus k due to independence and divided by probability t equal to small t. Since the distribution of summation j from 2 to n xj is Poisson with parameter n minus 1 into theta, after some algebraic manipulations, it finally reduces to the form tck into n minus 1 to the power t minus k divided by n to the power t, where k must be less than equals to small t. Hence, phi capital T, which is TCK n minus 1 to the power T minus K by n to the power T, is an improved unbiased estimator of G theta based on the sufficient statistic T. We consider our third example. Let x1, x2 up to xn be IID normal random variables with mean theta and variance 1. The PDF is given by f theta x equals to 1 by root 2 pi into e to the power minus half into x minus theta whole square, where x belongs to the real line. Suppose we consider a parametric function g theta equal to theta. Clearly, x1 is an unbiased estimator of g theta. Since the distribution belongs to the one parameter exponential family, here capital T equals to x bar equals to 1 by n summation j from 1 to n xj is sufficient for theta. Now we define phi x bar, which is equals to expectation of x1 given x bar equals to small x bar. The conditional distribution of x1 given x bar equals to small x bar is normal with mean small x bar and variance 1 minus 1 by n. It follows that phi x bar is equals to expectation of x1 given x bar, which is just equals to x bar. Hence, the Raw Blackwellized improved unbiased estimator of theta is x bar equals to summation over j from 1 to n xj whole divided by n. We consider our last example. Let x1, x2 up to xn be IID uniform 0 theta random variables. The PDF is given by f theta x equals to 1 by theta if x belongs to the interval 0, theta, and this is 0 otherwise. Here we consider the parametric function g theta equals to theta by 2. Since expectation of x1 equals to theta by 2, we choose x1 as an unbiased estimator of g theta. Now we know that x ordered n, which is equals to maximum of x1, x2 up to xn, is sufficient for theta. Now we define phi of x ordered n. This is just expectation of x1 given x ordered n equals to x ordered n. Now, given x ordered n equals to small x ordered n, the random variable x1 can take the value small x ordered n with probability 1 by n, and it is uniformly distributed over the interval 0, small x ordered n with the remaining probability of 1 minus 1 by n. Therefore, expectation of x1 given x ordered n equals to small x ordered n is equals to 1 by n into small x ordered n plus x ordered n divided by 2 into 1 minus 1 by n, which is equals to n plus 1 into x ordered n divided by 2n. Hence, phi of capital X ordered n, this is just n plus 1 into x ordered n divided by 2n, is an improved unbiased estimator of g theta, which is equals to theta by 2. In the present module, we have seen that a complete sufficient statistic provides the minimal reduction of the data. From the Raw Blackwell theorem, we have seen that in search for a uniformly minimum variance unbiased estimator, one should restrict to the class of all unbiased estimators which are based on the sufficient statistic. In the next module, we shall prove that if a complete sufficient statistic exists, then it will be the uniformly minimum variance unbiased estimator of its expectation.